Good evening, everyone, and a very warm welcome to the Astronomical Society of Edinburgh's December online meeting. I'm Neil Martin, President of the Society. And for those of you joining us on Zoom, please can you now ensure that your microphone is muted. We have a couple of items on our agenda this evening, as usual, for a mid-month session. And in a moment, I'll formally introduce our guest speaker for this evening, Dr. Tim Pearce. Following Tim's presentation and the Q&A, I'll close the session with a look ahead to what we have coming up over the next few months. So let's begin. Dr. Tim Pearce is a Stephen Hawking Fellow at the University of Warwick. His research is focused on debris disks around other stars, which are populations of asteroids and comets like the Asteroid belt and the Kuiper Belt in our own solar system. He has a particular interest in how exoplanets interact with this debris. Whilst Dr. Pearce's work is mainly theory, he's also heavily involved in observations using the James Webb Space Telescope, ALMA, and the VLTI. Dr. Pearce describes his career path as unusual. He completed a master's degree at Durham and a PhD at Cambridge, but then left academia for a while. He was selected to be an officer in the Royal Navy, where he specialised in engineering aboard nuclear submarines. He then went on to become a lead mathematical developer at a leading traffic modelling company. So I can see why there is the word unusual in there. Tim then returned to academia in December 2019 as a postdoctoral researcher in Jena, Germany. He then joined Warwick in November 2023 as a Warwick Prize Fellow and became a Stephen Hawking Fellow in May 2024. The UKRI Stephen Hawking Fellowship is a prestigious postdoctoral award in theoretical physics, supporting research that reflects Stephen Hawking's work in popularising science. So, ladies and gentlemen, please welcome Dr. Tim Pearce. Tim, I'll hand the control over to you.
Great. Thank you very much, Neil. Okay, I'm going to share my screen. Oh, I need to wait for you to stop. There we go. Excellent. Okay, can you all see my screen now?
Yep, perfect.
Excellent. And can you also see my mouse as well?
We can indeed, Tim. Yep.
Excellent. Okay, right. Okay, well, thanks a lot, Neil. So as Neil says, I'm an astrophysicist at the University of Warwick. And today I'm going to talk about the thing that I study, which is basically Kuiper Belts around other stars. Okay, so I'm going to talk, first of all, a little bit about what we mean by the Kuiper Belt. Then I'm going to talk about the fact that we can see these belts around other stars. I'm going to talk about the sort of processes that we think are going on in them and what that tells us about these planetary systems. Now, just before we begin, I think Will's mentioned in the chat, usually when I do these talks in person, I'm fine for people to just shout out questions as we go along. Because it's on Zoom, it might be a little bit more tricky to do that. So Will suggested that you can sort of send a message in the chat, and every sort of 5-10 minutes or something like that, I'll have a little bit of a pause and just see if there's any questions. And if not, there's question time at the end as well. Okay, so let's get going then. We're thinking about Kuiper belts around other stars. So the first thing to think about then is what we mean by the Kuiper belt. So let's go into our solar system. I'm going to start off with an image of what the solar system looks like today. And first of all, I'm just going to concentrate on the inner regions of the solar system. So here we've got sort of the inner regions. We've got the sun in the center, and then we've got our planets. And here I've just shown the planets out to the planet Jupiter. But as we know, these aren't the only objects in the inner solar system. We have all these other things as well. And this is what I've shown here. So these points are all basically asteroids. These are small bodies, solid bodies that are smaller than planets in the central regions of the solar system. Okay, so each of these small brown points is one of these asteroids. Now, when we think about these asteroids, I want to sort of get an image in your mind of what we're really talking about. So here I've got an example of one of these. This is the object Bennu. Okay, so this is an object that's about 0.5 kilometer across, and in a sort of asteroid scale, then this is a relatively small asteroid. Okay. And there's two things I want you to see when you're looking at this picture of Bennu. So the first thing is that this isn't a solid object. Okay, it's not like a big solid rock, like you might see in a film or something like that for an asteroid. In reality, we refer to them as like rubble piles. So you can see there's all these individual boulders, these individual rocks that are there. And essentially, this is a clump of these individual boulders and these individual rocks, which are sort of loosely bound together. So imagine you've got basically a big pile of these boulders, and their gravity is just enough to hold them all together into a single clump. Okay, so that's what to a picture. Not a single solid object for these small bodies, but really a loosely bound collection of rocks. The second thing I want you to notice is that Bennu isn't spherical. It's not like a planet. And the reason is because it's so small. As I say, this is only 0.5 kilometer across, which means that it doesn't have much mass. And if it doesn't have much mass, it doesn't have much gravity. And that means that it's unable to compact itself into a sphere. So the larger objects like planets, they're massive enough that their gravity compacts them into a sphere. With something small like this, you don't get that. You get these irregular shapes that can be sort of potato shapes or things that are non-spherical. But that's one thing to picture then. So that's a sort of smaller type of asteroid that we want to think about. At the other end of the scale, we've got larger things as well. So here we've got the larger object Ceres. So Ceres is about 1,000 kilometers across. Okay, so to put that in perspective, that's about 1/10 of the diameter of Earth. Okay, so you can fit roughly like 10 of these things across Earth. And you can see that Ceres now is different from Bennu in that it's more spherical. So it's massive enough that it's compacted itself into a roughly spherical shape. It's still not completely smooth. It's still not as massive as something like Earth, which has compacted itself right into a sphere. It's a little bit irregular, but you see it's much more spherical than Bennu. And Ceres and Bennu are both primarily composed of rock. Okay, so we're thinking of these also as rock, but Ceres also has some ice in it as well. There's some fraction of ice in there, but really you want to be thinking of these asteroids in the inner solar system as primarily rocky objects. Okay, so that's the sort of thing to picture when we're thinking about these bodies in the inner system. But obviously we've got asteroids throughout the system as well. They're not just located here in the middle. In the middle, they're mainly sort of concentrated in the asteroid belt. But if we zoom out a little bit, we can see that beyond the orbit of Neptune, so in this right-hand plot, we see the outer regions of the system. Beyond the orbit of Neptune, we have another belt. Okay, and this belt is much bigger than the asteroid belt. It's much more massive than the asteroid belt, and this is the Kuiper Belt. Okay. And so this Kuiper Belt is more what I'm going to be thinking about for the rest of this talk, and I'm going to talk about why in a second. But we've just talked about then what the planetesimals are like in the inner regions of the system. So we've thought about what the planetesimals are doing in the asteroid belt. If we think about what planetesimals to picture in the Kuiper Belt, we're more thinking things like comets. Okay, so this is an image of comet 67P. Again, this is relatively small, so you can see that it's not spherical. But a big difference between this and the object Bennu that we saw earlier on is that the comets have a much larger ice fraction. Okay, so you can see that in this image. You could see basically water ice being sort of sublimated off into space. That's what these things here. So the ice is essentially sort of boiling away as you got close to the sun. So we've got a much higher ice fraction there. Now, this is a relatively small object, and then at the other end of the scale, again, we've got the much larger objects. So here we've got the Kuiper Belt object Pluto, which again is much larger. It's now spherical in shape, and this has quite a large fraction of ice. Okay. Now, just while we're here, obviously there's been this sort of debate for a little while about whether Pluto is a planet or is a smaller object. I'm on the side of the sort of astronomical community here. Okay, so the way to picture Pluto isn't really as a planet because there's many Plutos in this Kuiper Belt. There's multiple different objects. The way to think about Pluto is to think of it basically as like a big comet. Okay, because there's lots of other nearby objects which are only slightly smaller or even slightly bigger than Pluto, and they're sort of immersed in a sea of smaller bodies as well. So the way I picture Pluto is basically as sort of a large comet as opposed to a small planet. Okay. So that's what we're sort of picturing when we think of the objects in the Kuiper Belt. Okay, so the main difference so far then to say is that in the asteroid belt, in the inner regions, objects are mainly rocky. And in our Kuiper Belt, in the outer regions, objects are more icy. Okay. And the way to think about why that is basically because the Kuiper Belt is further away from the sun, so it's colder, and that allows these sort of more fragile materials, we call them volatiles, like water ice, to survive. Because if the bodies were too close to the sun, then the water ice kind of sublimates away, basically boils away into space. Whereas in the outer regions in the Kuiper Belt, you're allowed to have a lot more water ice there. Right, okay, so that's a very quick summary of our own solar system. Okay, and I've focused a little bit on the asteroid belt, but really I want to focus more on the Kuiper belt. Okay, why do I want to do this? The reason is because it turns out we can see Kuiper belts around other stars as well. Okay, and that's what we've got imaged here. So I'm going to spend a little bit of time on this slide to really sort of emphasize what we're seeing. So first of all, each of these panels, each of these individual panels shows a different star system. Okay. These are telescope images. In this case, these are radio telescope images. So they're false color images. In each case, you've got the star located at the very center of the panel. Okay. In some cases, you can see the star. In other cases, you can't see the star. It basically depends on the type of star and the specific wavelengths that this telescope operates at. Okay, but in all cases, the star is here in the center, even if you can't see it. Now, what you can see, though, in every panel is you can see something that looks a bit like a ring. That is basically a Kuiper belt located around a different star. Okay. Now, the first thing to say is that we're viewing all these belts at different angles. So some of these belts we're seeing face on, like this one. Some of these belts we're seeing edge on, like this one. That obviously just depends on like the viewing angle that we happen to see the system at. But even if you take that into account, okay, even if you take into account the fact we're looking at this at different angles, you can see that we still have a broad diversity of shapes and features in these belts. These belts don't all look the same. So to give you some examples, some of these belts like this one over here are very broad, they're very wide. Some of them like this one over here are much narrower. Some of them have got features like this one has a gap in the middle. This one over here is elliptical. It's not circular, it's elliptical in shape. And I'll come back and talk about several of these systems later on. But the thing to convey here is that we can really see these belts around other stars and they all look different. There's very few that look alike. Okay. And then the final thing I want to say just on this is that to give you a little bit of a sense of scale, each of these panels has a bar, has a gray bar like this at the bottom. This bar is roughly the radius of the Kuiper belt in our own solar system. Okay. So if you look at a system like this one here, this is a belt that's roughly the same size as our Kuiper belt. But we also have some that are much larger, like this one over here. Our Kuiper belt would only be sort of down here in this image, but we've got a belt that's sort of 3, 4, 5 times larger. Okay. So typically the belts that we tend to see are roughly the scale of our Kuiper belt or like several times larger. These images aren't sensitive to asteroid belts, and so that's why I'm talking about Kuiper belts in this talk. Okay, so we're thinking about basically things in the outer regions of the planetary systems. Right, so these are real images of extrasolar Kuiper belts. You can also see that some of the image quality varies. So we've got some that have got very sharp images like these ones here, but we also have ones that are much more blobby. And that's because basically we've got some of these belts are much further away. They're also much fainter, which means they're harder to image. So you generate essentially a noisier or blobbier image. Okay. But what I want to emphasize is that in some cases, we've got really, really good images. We've got really sort of pristine images. So if I show you this one, this is a different instrument. This is now the James Webb Space Telescope. And this is showing you in quite exquisite detail the Kuiper belt around another star. Okay, so first of all, the star's located in the center. this black region here, this is a physical mask that's been placed over the star to stop its brightness overwhelming the disk. Okay, it's a coronagraph. So ignore that sort of black bit there, that's artificial. But what you can see is you can see these very sort of exquisite dust lanes in these systems. You can see one here, and you can see another smaller dust lane over here. Okay. Now, this is the level of detail that we can now image other systems in. So it really is sort of a really obvious planetary system. And this gives people like me, people who work on sort of theories and things like that, this gives us loads of really good quality data that we can now test and expand our theories on. Okay, so that I think is a good point to briefly pause and see if there's any questions so far.
No questions, Tim?
That's fine, well, don't worry. I say if people want to ask as they go along, please feel free to message me in. But yeah, don't worry, we'll have time at the end as well. Okay, so far then, basically, I've mentioned the fact that we have the Kuiper Belt in our own system, and then we can see Kuiper Belts around other stars as well. So the next thing I want to say is, well, what's actually going on in these belts? So what should we be picturing when we imagine a Kuiper Belt either around our own star or around another star? And the thing I want to show is just this cartoon here. So this is just a cartoon, but it actually turns out it shows basically everything you need to know about these Kuiper belts. Okay, it shows all the important processes. And what I'm going to do throughout this talk is I'm going to sort of pick part of this diagram and I'm going to talk about it, and then I'm going to come back and return to the diagram and then pick a different part to talk about it. So let's get started on that then. What are we picturing then when we think of one of these belts? So we've got the star, and then orbiting the star, we've got a belt of these objects. Okay, these we call them generally planetesimals, and I've already said planetesimals a few times tonight. Basically, a planetesimal is like a solid object in a planetary system which is smaller than a planet but larger than like a dust grain or something like that. So basically, if you hear planetesimals, just think of asteroids or comets. Okay, so we've got a belt of asteroids or comets which is orbiting the star. Now, these planetesimals, these asteroids and comets, as they orbit, they collide with each other. And when they collide violently. Okay, so you get collisions like this. And what these collisions do is they break the bodies apart. So the bodies don't stick together, the bodies don't bounce off each other, they physically shatter when these collisions occur. They're violent, high energy collisions. Okay. And then when you have a lot of collisions, what happens is each of these collisions produces dust. Okay. And so what that means is we've got all this dust floating around. And so these planetesimals are now orbiting in a sea of dust. Okay, they're like embedded in this sea of dust. And then the last thing on this diagram is we might have nearby planets. So in the Kuiper Belt, we've got Neptune, which is very close to the inner edge of the Kuiper Belt. Similarly, in these extrasolar systems, we believe we have planets there as well. And if there's planets that are located near these belts, then they're going to interact with the belts. Okay. So what I'm going to do now for the remainder of the talk is I just want to talk about these 4 parts that I've labeled on this diagram. So we really get a good understanding of what's going on in these Kuiper belts. And I'm going to start off with what's arguably the most boring of these 4, which is the dust. Okay, I'm going to start off thinking about the dust. Now, dust doesn't sound as exciting as sort of planets or collisions or planetesimals, but dust is important. Okay, and the reason that dust is important is because the dust is what we see. So when we're looking at an object like this, we can see these sort of exquisite like features and things like that. What we're actually physically seeing here is dust. We're seeing the light that's reflected or emitted from dust grains. Okay, we're not seeing the light that's reflected or emitted from the larger bodies like the planetesimals. And I'm going to show you why with an example from our own solar system. Okay, so as you'll recognize, this is the planet Saturn, imaged by the Cassini spacecraft. And as we all know, Saturn's got these sort of very well-defined, very bright rings around it. Okay, these are really bright, bright enough that basically anyone can use a sort of relatively small telescope and they can see the rings of Saturn. Okay, these are really sort of bright objects. But the really interesting thing to me about this is that whilst the rings are really bright, the total mass in these rings is tiny. So if you were to take all of the mass in Saturn's rings and you were to squash them down into just a single object, okay, a single solid object, then that object is going to have a mass that's less than half that of the small moon Mimas. Okay. Now, where's Mimas on this image? Mimas is down here. It's that little dot, which you may or may not even be able to see on your screens. Okay. So to repeat that, all of the material in all of the rings of Saturn has a total mass that's less than half that of this little dot down here. But we can see the rings really clearly, and we can barely see Mimas. And the reason is because all the mass in Saturn's rings is basically spread into loads of different particles. It's spread into lots of different bodies that are all very small, but it means collectively they cover this huge surface area. Okay, they've got a huge area, and what that means is that they're really good at scattering or emitting light. Whereas Mimas down there, Mimas may have more mass, but Mimas has a comparatively small surface area because lots of that material is locked up inside Mimas as well. So that means it's much worse at scattering and emitting light. So the rings are really clear because it's basically broken up into loads and loads of small objects, whereas the larger bodies like Mimas are much harder to see. It's exactly the same in our Kuiper Belts, our extrasolar Kuiper Belts as well. We've got all of this dust, which doesn't have much mass in total, but what it does has is a huge surface area. So the dust is really good at scattering and emitting light. Whereas the larger objects, the planetesimals, they've got much smaller surface area. So basically we don't see them. So when we look at images like this, what we're seeing is the light that comes from the dust. We're not seeing the light that comes from the planetesimals. Okay, so that was the next bit about dust. I can see there's been a couple of questions come in. Do we want to pause briefly here, Will, and see what's going on
Yeah.
there?
What I suggest is if Ian could unmute and ask your question, Ian, and we'll hold marks till the end if that's okay.
I suggest you just ask Ian's question, Will.
Sorry,
Oh,
sorry, I'm back. Yes, the near the bottom right, you showed an elliptical, or what appeared to be an elliptical orbit of Kuiper Belt objects. So how do you differentiate between an elliptical Kuiper and a star system at an angle?
good question. So I was potentially going to mention this later on, but I'll mention it now to clear it up. So the reason we know this is elliptical rather than a circle is because this point here is the star. Okay. And you can see that the star isn't located in the sort of center of the disk. If it was, it would be more like here. You can see it's slightly offset. Okay, so what that tells you is that even though we're seeing, as you say, the image at a tilt, it can't just be a circular thing that we're seeing at a tilt. It has to actually be really elliptical because the star should always be in the center if it's circular.
Right.
That's how we know.
Okay, thank you.
There is.
And Jim, if you'd like to unmute and ask your question, please.
Yes, you said that the collisions are violent. I'd have thought that distance, that the relative velocities would be quite low between bodies. So what causes a high enough relative velocity between bodies to make the collisions violent enough?
Yes, so this is something that I'm going to come back to again later as well. What this is we think that some process has happened which has basically excited the bodies up. Okay, so we think that potentially, like an example here, is that you might have a planet which is located near the disk. And what the planet does is its gravity basically is able to perturb the planetesimals they're orbiting in the disk. And that kind of excites all their orbits up so they can start colliding violently with each other. That's what we think, or that's one of the things that we think might be happening. I will talk about this towards the end of the talk as well, to shed a little bit more light on it. But yeah.
Okay, thanks.
Great stuff, Tim.
Okay, get back to where we got to. So, okay, we asked the question then. We said we've got this dust. Where's the dust coming from? So what's holding the dust in the first place? And so we're going to bounce then from the dust over to the planetesimals. Okay, so we mentioned that we have these planetesimals, these asteroids and comets in our own system. Okay, so then we can guess just by basically assuming that our solar system is relatively typical, that we're going to have things like asteroids and comets in these other systems as well. The problem is, though, we can't really directly see them. As I've mentioned, we can't see the light that's coming from these bodies because they're too small. What we can do, though, is we can use other means to infer that they're there. So just to recap, these are the sort of bodies we have in our own solar system. We've got sort of Bennu as an asteroid, we've got our IC67P, we've got our Pluto object. We probably think that we have all of these things in extrasolar systems as well. Now, I'm going to give you an example of one of the bits of evidence that we have which suggests this is correct. So here we've got a graph. So on the horizontal axis here, this is time. It's time measured in days from some point. Okay, so it doesn't matter what the actual numbers are, but you can see that we're dealing with about 3 days worth of data. Okay, this is about 3 days worth of data on this line. And then on the vertical axis, we've got the brightness of a star. Okay, so what's happening is that each of these black points here, this is a measurement that's been taken over a period of about 3 days, and it basically tells you how bright the star appears to a telescope on Earth. Now, what we can see is after a period of like roughly a day or so, suddenly we have a sort of quite dramatic dip in the star's brightness, followed by a slower return to the original brightness. Okay, now this, as some of you might have come across before, is we think it's a transit of an object. So basically, we think what's happening is that you've got the star, and then you've got some object passing in front of the star. Okay, and that's blocking out a little bit of the star's light. So the object starts to pass here, it blocks out a little bit of the light, then it starts to move away from the object again, so it starts to unblock that part of the star, and the star's brightness returns to normal. Now, this is frequently used, this method, to detect planets around other stars, but this isn't a planetary transit. The reason we know is because when a planet goes in front of a star, it makes a U-shaped transit. Okay, so it's a sort of symmetrical U-shaped transit. Whereas you can see this is an asymmetrical transit. It's got a much sharper start and a much slower finish. What's actually making this transit is not a planet, but a comet. Okay, this is a comet around another star. So the thing to picture is an image like this here. So we've got comets passing in front of the star, they block out a small amount of light, and what happens is you imagine you've got the sort of rocky nucleus of the comet comes in first. So when that passes in front of the star, you get quite a dramatic drop in the starlight, and then the nucleus sort of moves away, but then you have this long fuzzy tail afterwards, okay? And the fuzzy tail is much larger than the nucleus, and that basically means that it takes much longer for the tail to move out of the way. So that's why you end up with this sort of not symmetric U-shaped transit, which is what you expect from a planet. This is a transit of a comet. So this is direct evidence that we have comets around other stars. We also have another bit of evidence, which is that I mentioned before, when we look at these systems, what we're seeing is the dust. Okay. The problem we've got is that this dust shouldn't last for very long. I'm going to talk about this little bit more in a second, but this dust should actually basically get destroyed really quickly. It should get destroyed and sort of disappear from the system really quickly. So the fact that we see this around lots of stars, in fact, we can detect these disks around at least a quarter of stars, this implies that you've got some process which is continuously replenishing the dust, because otherwise it would just disappear straight away. This can't be dust that's just left over from planet formation. This has to be dust that's continually being replenished. Now, in our own solar system, we see that there's loads of dust, and this dust is basically released through collisions that we can directly observe between comets or between asteroids. And so we think that similar things are happening in our extrasolar systems as well. So we think that our planetesimals are colliding together and they're releasing dust. Okay, I can't see any other questions at this point, so I'm going to move straight into the next part, which is to talk about these collisions. So these collisional processes that are happening. So the picture to have in one of these systems, the picture to have in one of these belts, is something we refer to as the collisional cascade. So what we've got is, imagine that we've got two asteroids or two comets, two of these planetesimals floating around, and these collide together, and when they collide together, they break up into smaller objects, okay? And then these smaller objects collide with each other and they break up into smaller objects, and this process keeps going until you eventually grind your material down into dust. Now, when you get to dust sizes, the physics starts to change, okay? The reason the physics starts to change is because now when you get dust grains that are really small, they're small enough that just the wind from the star is sufficient to blow those grains away from the star. Okay, so if you've got like a big object like a planet or an asteroid, that doesn't really feel the wind. But if you've got a really small thing like a dust grain, that does feel the wind, and that wind is actually powerful enough to overcome gravity and blow the dust out of the system. And that's a process that we call blowout. And in fact, I've mentioned wind first because wind is sort of the most conceptually easy way to think about this. But actually, it turns out wind for most stars is a secondary process. It turns out that the thing that's most able to blow the dust out of the system is just the light itself. So just the force of the photons just hitting the dust grains is enough to blow these small grains out of the system. Okay. So this diagram is basically, the thing to picture is like the life cycle of material in our Kuiper belts, in our extrasolar Kuiper belts. So you've got objects colliding together, grinding down, getting down to dust, and then the dust is getting blown away from the star. Now, if you think about it, we're not adding any more mass in. We're busy starting off with the planetesimals that we were born with, and then they're grinding away into dust, and then that dust is getting blown away. And what this means is that we're continually losing mass from our belts. So our belts are just decreasing in mass over time. They're basically just eroding away with time. And we can see this when we look at the data. So here we've got another plot, and this basically shows you all of these Kuiper belts that we've seen around other stars. So on the horizontal axis, first of all, this is the age of the star that we see the belt around. So we've got young stars at this end, and we've got old stars at this end, okay? And then on the vertical axis, this is how bright our belt is. In fact, technically, it's how bright the belt is divided by how bright the star is. So it's like a sort of fractional brightness. And then each of these blue points, this is a Kuiper belt that we've seen around another star. And you can see that these aren't just randomly sort of placed on this plot. You can see that stuff tends to start off bright. So the young objects up here lie towards the top of the plot. And then when you look at the older objects here, they're lower down the plot. Okay. And this is because belts are becoming fainter over time. They're dropping in brightness over time. And the reason they drop in brightness over time is because they're losing mass, they're losing dust, they're losing brightness, okay, with time. So this is literally a plot that shows how over the age of a star, these belts basically grind themselves away, they erode away. Now, just as a sort of point of interest, if I was to add our own solar system onto here, then we're all the way down here, okay? So the asteroid belt and the Kuiper belt, even combined, are much, much fainter than the belts that I showed you earlier. They're much fainter than the belts that we're detecting around other stars. And in fact, our belts are so faint that it means that if they were located around another star, we wouldn't be able to see them with our own technology at the moment. Okay, they're too faint. So we don't actually know why this is. We don't know whether it turns out we've got a load of other extrasolar belts, they're all located down here on the plot, that we just can't detect with our current instruments. So our current telescopes can only detect down to about here, where the blue points stop. It could be that we've got a load of other fainter objects down here, and our Kuiper belt is a typical one of them. But it could also be that our Kuiper belt is weird in some way. And actually, there's evidence in both directions. There is evidence that our Kuiper belt is strange compared to extrasolar Kuiper belts. I'm not going to talk about that now, but I could talk about that in the questions if people are interested. But basically, belts that we see around other stars, they first of all get fainter over time because they're eroding away. And also they're much brighter still. Even the very faintest ones we detect, they're still much brighter than our own Kuiper Belt, which is sort of weirdly faint. Okay, so I'm going to quickly go back to, I believe it was Ian's question earlier, or was it? Ooh, it might not have been Ian. This was the question about why the objects are colliding together violently. Okay, so this is a bit of an explanation to that. But the short answer is we don't quite know, but we've got some theories. So as we mentioned before, we know that in our belt, we have these asteroids, these comets, which are colliding together, and they're colliding together violently because they're shattering and they're releasing dust, and the dust is what we see. So the question is, why are these violent collisions happening? Because as was said earlier, we're in the outer regions of the systems. Things generally move quite slowly in the outer regions of the system, so you'd think the collision speeds would be quite small, but that's not the case. That's not what we see. We think the whole system probably did form with quite low collision speeds though, but we think later on something happened to sort of excite all these bodies up. So we think that some process happened which caused the collision velocities to grow, caused the orbits to change and caused the collision velocities to grow. And whatever that process is, we refer to it as stirring. So imagine like you've got quite like a smooth cup or something like that, and then something comes along and it stirs it all up. And that causes these orbits to excite, it causes these collisions to happen. So that's the sort of general idea behind stirring, but we don't quite know what's happening. Okay, but there's several theories, as I mentioned. So imagine, first of all, here we've got a diagram. So we've got the star in the center, we've got our disk here, so we've got our belt, and then inside our belt, we know that our larger objects, our asteroids and comets, are colliding with each other to release the dust that we see. So we think that something has to have happened to perturb their orbits, to basically excite or affect their orbits to make them start violently colliding with each other. There's several suggestions for what this could be. One suggestion is something we refer to as self-stirring. So this is the idea that we have bodies, larger bodies like Pluto-sized objects that are located in our belt. So basically the very biggest objects in our belt. And they might have enough gravity to be able to perturb the smaller objects around them. And so it might be that you've got embedded Plutos which are going around stirring your smaller comets, your smaller asteroids, and that's causing these violent collisions to happen. So we refer to that as self-stirring because that's kind of the belt itself is doing the stirring. So that's one possibility. Another possibility is something we call flyby stirring. So this is the idea that at some point in the star's life, probably early on in the star's life, another star passed close to it. And obviously another star has a huge gravitational field, and that would be able to, again, basically perturb the orbits of the bodies in the belt, and that could then ignite this collisional cascade we talked about earlier. It could ignite this, these violent collisions between the bodies. Because once they start, they don't stop. So you just have to get them going in the first place. And then the third possibility, and this is the one I mentioned earlier, is planet stirring. So the idea that we would have a planet which is orbiting, like Neptune does next to the Kuiper Belt, close enough that its gravity is able to sculpt the belt and affect the orbits of the bodies in the belt. And that can be another way to dynamically stir at the disk. And that would now lead me on to my final part of the talk, which is talking about planets. But before we do that, I see there's another question, so I think I'll pause there for a sec.
Yeah, Ramsey, if you could unmute and ask your question, please.
Yes. I was wondering if any um, record rather of a Kuiper Belt processing around a star had been recorded.
So it's not been directly recorded, and the reason is because the timescales would just be too long. But what has happened, and this is actually directly where I work, it has been predicted. So if you have planets, for example, near these belts, or even if you just have a massive belt which affects itself, it's able to process around the star. So for people who don't know what processing is, basically imagine you've got like an elliptical orbit, And you've got your star and you've got an elliptical orbit. The precession is when the orbit itself moves over time. So like imagine you've got an elliptical belt, the belt itself moves around the star over time. We predict this to happen, okay? But the problem is the timescales will be thousands of years at least, possibly longer, possibly millions of years in some cases. So it's not something we can hope to directly observe. There are potential sort of ways that we can infer that it's happening. So one possibility is that when these belts precess, their inner edge should precess at different speeds to their outer edge. So you'd end up with a belt basically shearing out, if that makes sense. It would get wider over time. So there are belts where we can look at them and think, well, maybe this has or hasn't happened, and that can be evidence for precession having occurred. But unfortunately, yeah, because we're dealing with really probably millions of years of time scale for this precession to actually occur, it's not something we can directly observe, just infer.
Okay, I was thinking it would maybe happen more in the scale of the rings around our planets
Yeah, so
in that time scale.
exactly. So rings are kind of small scale analogs to these belts. There's two key differences between something like Saturn's rings and one of these belts, though. The first, as you mentioned, is basically those rings are much closer to the planet. Everything happens much, much faster. So you can observe precession over periods of years or something like that. You can easily see it's happening. That's one difference. And the second difference is actually a physical difference in how they behave. In those rings, the collisions are much slower. So actually, when objects in, say, Saturn's rings hit each other, they don't shatter like this collision here. They more just bounce off each other. Okay, and that's actually why Saturn's rings are so thin, because every time they bounce, they lose a bit of energy. And so even if you start off with Saturn's rings quite thick, you've got everything bouncing and bouncing and bouncing, and it loses energy, and Saturn's rings get very thin over time. That doesn't happen for these Kuiper belts because the collision speeds are much, much faster. So instead of bouncing, you get this shattering effect. But they're the two main differences. The difference, first of all, is that everything happens much faster in like Saturn's rings, and the second difference is, yeah, the collision speeds are much, much lower in Saturn's rings than they are in one of these belts.
Thanks very much.
Okay.
And Gillian, if you'd like to unmute and ask a question, please.
Yes, I'm not quite clear why you're getting radiation from the dust. It's presumably it's long wave like you showed radio. Is it because it's very slightly warm, or is it reflected radiation from the sun or the star?
It's actually both, and it depends which instrument you use to look at it. So the images that I've mainly showed so far, these are images that show thermal emission. So these are longer wavelength images. So either they're radio or they're around sort of the millimeter wavelengths, or we've got some far infrared as well from James Webb.
Yeah.
Okay, but these are basically longish wavelengths. And that is like kind of infrared on Earth. It's basically showing you the heat that's sort of given off by these bodies. And that's in fact why in those images the star doesn't appear very bright, because the star doesn't emit much in those wavelengths, whereas the dust emits quite a lot more because the dust is much cooler than the star, so it emits at much longer wavelengths. So that's one thing. But another set of images which I've not shown here are things by, for example, the Hubble Space Telescope. So the Hubble Space Telescope, that shows actually sort of optical wavelengths of light, so the light that we would see with our own eyes. And that shows light that's directly reflected off the grains. So we can see those as well. So you actually get both scattered light and emitted light. And the interesting thing is that those images, they're actually showing slightly different grains. So if we look at the scattered light, we're mainly seeing the really small grains, because we tend to see grains that have the same size as the wavelength that we're looking at. So if you look at short wavelength, you see small grains. And if you look at big wavelengths, you see big grains. But I mentioned earlier that the dynamics are different between these grains, because you start to get the wind and the radiation from the star affects the small grains but doesn't affect the big grains. So what that means is by comparing images of scattered light and thermal emission, it's showing you two different populations of grains. It's showing you two different sets of physics that are going on, and that allows you to learn a lot more about the belt than you would if you just used one. But yeah, to answer your question, Gillian, it's basically we can actually do both. We can do thermal and scattered light.
Thanks.
And finally, we just got one last question. If you could make your question fast, Mike, please.
Questions fast, sure. Hi Tim, great talk. I'm curious as to what defines fast for the collisions. It's got to be relative to something.
So it's relative to the strength of the bodies. The answer you're looking for is that if you have a body that's made of ice, or a body that's made of rock, then the collision speed you need slightly depends on the size of the body, right? So if it's like a really small body, it's held together by its own strength. If it's a really big body, it's held together by its own gravity. And you end up with sort of a slightly complicated shape, which is basically that you end up with bodies that are about 100 meters in size being the weakest. Okay, so they're the weakest. If they're smaller, they're better able to hold themselves together by their own strength. If they're bigger, they're able to hold themselves together by their own gravity. So 100 meters are the weakest. To break up a 100-meter body of pure rock or of pure ice, you need to collide at roughly 100 kilometers a second. Something like that. Sorry. No, 100 meters a second. Not as bad as it sounds. 100 meters a second. Okay. So it's not too fast, but it's still faster than we expect from our system formation theories. So the numbers to have in mind, about 100 meters a second.
And 100 meters per second compared with orbital velocity is 10 times, or roughly what?
So it's something, I'll have the number somewhere.
We can leave that till later, it's fine.
Yeah, I think you're going to be at about 1% or so, but I wouldn't want to give you wouldn't want to commit without doing some maths, but I have it somewhere. But yeah, 100 meters a second is what we're thinking.
Thanks.
Okay, no worries. Right, okay, so what I'll do now is I'll move on to the very last part of the talk, which is the thing that I actually study, which is planets. Okay, so we mentioned that we might have planets near these belts. So we know, for example, that in our own solar system, our belts are very clearly linked to planets. Okay, so we can see that sort of the shapes and the structures of both the asteroid belt and the Kuiper belt are clearly linked to the orbits and the locations of planets. And in fact, they're so clearly linked that if I was to remove the planets from this plot, you'd still be able to tell me where the planets are just based on the shapes of the belts. So to give you some examples, so let's start off in the inner region here. So we've got the sun here, and then we've got this big gap here between the asteroid belt and the sun. So I'd guess that there's planets located in that belt because there's not that many asteroids here. Okay, so we think probably the asteroids that would have formed there have either been accreted into planets or they'd have been scattered by the planets and thrown out of the system. So I would guess, just looking at this, that we've got planets in this gap. I'd also guess that there are probably multiple small planets. And the reason for that is that we've still got some bodies here, right? It's not completely devoid of asteroids. There's still things here. Now, if you had one big planet, like if you had Jupiter here or something like that, Jupiter would be really, really good because it's so massive at scattering material away. So Jupiter would be really good at just clearing out this and creating a void with no asteroids at all. But we don't see that. We still see asteroids here. So that what that says to me is that instead of one big body, which has cleared away everything, we'd have multiple smaller bodies. Okay, so I'd imagine there'd be multiple small planets located here. Then if I move out a bit, we can see we've got the asteroid belt now, and you can see that the asteroid belt doesn't have any major gaps in them. It does have little gaps. It's got things that we refer to as the Kirkwood gaps, but really they're tiny. Like on an image like this, you can't see them. That tells me that there's not a planet located in the asteroid belt itself. Because if there was one like here, for example, then it would carve out a hole, which would turn into a gap. So you'd end up with a gap around the asteroid belt like that. We don't see that, so that tells me there's no planets in the belt itself. And then moving out further, you can see now in the outer regions of the inner region, if that makes sense. So beyond the asteroid belt, you can see we're very devoid of planetesimals. We don't really have many at all. And the planetesimals we do have are occupying these well-defined structures. So what that tells me is, first of all, that there's a big planet out here because this planet has been able to remove loads of the planetesimals. We can also see from the shapes and of these sort of planetesimal populations and the sort of dynamics that we understand, we'd be able to say not only is there a large planet located somewhere out here, but also that planet has to be located here, because that's the only way you get these characteristic shapes that we see here. And then sure enough, if I put the planets back on, this is exactly what we see. So we basically used just the dynamical features of the dust that we've seen in the inner system. We've used that to infer where the planets are. And similarly, we can do the same in the outer regions as well. We've got the asteroid belt over here, and then we've basically got a big gap between the asteroid belt and the Kuiper belt. And again, you'd infer, if you just looked at this without knowing anything about the solar system, that gap is probably containing multiple planets. And then sure enough, we can add them back in, and there the planets are. Okay, so the main thing I want to get across here is that the belts in our system are very clearly linked to where the planets are in our system, and that we should be able to just look at the belts and infer where the planets are, even if we didn't know where they were. So why is this important? It turns out it's important because we see all these shapes and features that we mentioned earlier on. We see these gaps, we see these like elliptical belts and things like that. We think these are caused by planets as well, okay? We think that there's extrasolar planets that are located near these belts. But much like our planetesimals, we can't see the planets themselves, okay? Because the planets, again, are too faint, but we can see the dust. So what we can do is we can try and use the patterns that we see in these belts to try and infer the presence of planets that we otherwise wouldn't be able to detect in the outer regions of these systems. So how would these belts actually interact with the planets? So on this next slide, what I'm going to show you is I'm going to show you lots of different ways that planets can interact with belts. Okay, so I'm not going to go through them all, but I just want to basically emphasize that there's lots of different things that can happen. Okay, so each of these sort of panels shows a different interaction. So just to give you some examples, we've got a star here, and then we've got a belt. And in this case, we've put some planets on our belt, and our planets are able to carve out a gap in our belt. So that's one thing they can do. Planets can also do things like drive spiral structures in our belt. They can make clumps appear in our belt and things like that. Okay, there's lots of different things that can happen. Now, as I say, we can't see the planets in these interactions because they're too small. But what we can do is we can sometimes see these structures. Okay, and so what I specifically do, and people like me, is we use our knowledge of dynamics and our computer simulations to be able to look at belts where we see patterns or features in them, and then work backwards and infer what planets we think are causing them. Okay, so I'm going to give you a couple of examples of this. So first of all, here we have a Hubble Space Telescope image. This is a scattered light image for Gillian. This is an image of the Beta Pictoris disk. Okay, so I need to explain this slightly. Here, the star is located here, and once again, it's been masked out by a coronagraph. So this rectangle here, this is just an artificial thing that's been placed on the Hubble Space Telescope to block out the starlight so we can see the disk. Okay, so ignore the rectangle, but the star is located under the rectangle. And then we've got this sort of false color image, obviously, but out here, this is our disk, and we're seeing this edge on. So this is like an edge on system, okay? Now ignore the outer regions of the image because the outer regions basically get a bit more noisy. So this stuff isn't real out here. This is just noise. But the thing that is real is that we have this weird shape. So we've got the sort of flat disk out here, but then this side of the disk is sort of warped upwards. So we see that there's like an overdensity here. And if we follow that down, it goes through the star. Then on the opposite side, there's an overdensity underneath the disk. And then you return to the original disk out here when you're far away from the star. Now, when people first detected this, they were interested in what it was. And the first idea that people had to explain this was you can do it if you've got a planet which is on a tilted orbit. Okay, so this is a diagram of it. Here's the star, here's the planet, and its orbit is tilted relative to the plane of the disk. Okay, and what happens if you've got a tilted orbit is your planet's gravity basically tries to grab the disk and pull it along with it. So the planet wants the disk to lie with the same tilt as the planet. Okay, so close to the planet's gravity is stronger, so it's able to grab the inner edge and basically puff it up like this, and that's what you see. But then further away from the planet, the gravity is much weaker. So basically the planet doesn't really have much effect on the outer part of the disk. So what you end up with is you end up with this warped structure like this. Okay. So this was the idea that people had based on this image. A few years later, then people looked at the star again. This is a different instrument this time, and sure enough, they found the planet that they thought was driving this warp. So in this case, the star is located here. Again, it's hidden under a mask. It's hidden under a coronagraph. This is a superposition of several images with the disk out here. But what you can see is this little white point here. This is a planet. This is a directly imaged planet, which has exactly the orbit and the mass that we thought it must have based on this warping out here. So this is an example of where we can actually do this. So you can look at a disk that's got a feature in it, and you can infer the planet that we think is driving that feature, even if we originally couldn't see the planet itself. Now, just very quickly, I've got two more examples. The first one to show you is, this is another system with a gapped disk in it. Okay, so here the star is located in the center. This is kind of an inverted color image. So imagine the black should actually be white and the white should actually be black. So the disk is located here. Okay, and you can see that we've got this disk and it's got this relatively shallow gap in it. Okay, the easiest way to generate a gap like this is if you have a planet which is embedded in that gap, and that planet has moved over time. So this is a simulation that one of my old students conducted, where basically showed that if you were to place, in this case, a Neptune-sized planet, which is too small to see directly, if you were to place a Neptune-sized planet in this disk and have it move a little bit, which is something we expect to happen in this disk, then you can produce something that looks quite a lot like the observation, even though you can't see the planet directly. And then the final example I have is this one here. So this is this elliptical object that we mentioned earlier. So I mentioned again that it's elliptical because the star is not located in the center of the disk. It's offset. So that means it can't just be a circular one that's tilted. It has to be an actually elliptical disk. Again, the easiest way to generate an elliptical disk is if you have a planet that's on an elliptical orbit nearby it, because the planet, again, will try and drag the disk into an orbit which kind of matches the orbit of the planet. So again, this is another system where we've looked at it, we've generated this prediction, and now the interesting thing is these predictions were all made before the James Webb Space Telescope launched. So now we have several programs which are looking at all of these disks, and they're attempting to spot the planets or rule out the planets that we've inferred in these systems. Okay, so sort of stay tuned for this. This is us like actively now trying to test the theories that we've been running on for a little while. Okay, so I've got one more slide to show you before my conclusions, which is basically to answer the question, why does this matter? Like, why do we even care that we can see the planets around, well, that we can see the belts and we can use them to infer planets? The reason is because those planets, as I mentioned, wouldn't be detectable without doing this. So to show you what I mean, I've got the final plot to show you. So on the horizontal axis here, this shows you distance from a star. Okay, so stuff that's close to a star is on the left side of the plot, as stuff that's far away from the star is on the right side of the plot. Okay, so that's distance from the star. Then on the vertical axis, we've got the mass of a planet. So low mass things are down at the bottom and high mass things are up at the top. So if I add our own solar system planets on, hopefully that makes a little bit more sense. So we've got like Mercury, Venus, Earth, Mars over here, for example. This is what the solar system would look like on these axes. Now we've also got these various other means of detecting planets around other stars. And if we use these, then these are the planets that we get. So these planets are things that have been directly detected through things like the transiting method I mentioned earlier, where the star passes in front of the planet passes in front of the star. Or there's the radial velocity method, where the star basically wobbles around a little bit when a planet goes by. But the key thing to notice is basically all of these detected planets lie in this region of the plot. Okay, they're all massive things, they're all massive planets, which are located quite close to their stars. And that's because it turns out they're the easiest ones to detect using their methods. So if you imagine a transit, if you've got a really big planet like Jupiter passing really close to a star, that's going to block out loads of light. So it's easier to detect that If you've got a small planet like Earth and it's located like where Neptune is, that's going to block out a tiny amount of light. So you basically just don't detect it using this method. So for that reason, all of these methods so far are biased towards finding big things which are located close to stars. We've got this big gap out here, smaller things which are located further away from stars. We don't really detect anything there, and it's not because we don't think those planets exist, it's because our methods are just not sensitive to them if they did exist. But this is where these belts come in, okay? Because this is the region where in our own solar system, the Kuiper Belt lives, and where in these extrasolar systems, these extrasolar Kuiper Belts live. And we said that we can use these extrasolar Kuiper Belts to infer where the planets are in these systems. We can infer the presence of planets near these belts. And if we do that, then we end up with these points here. So these red points are all planets which have been inferred to exist based on the belts. And they all lie in this region where we basically wouldn't be able to detect them otherwise. So this is the part of the reason why people are so interested in these extrasolar Kuiper belts, because they allow you to probe the outer regions of planetary systems where we otherwise are not able to detect planets directly. And these are things that things like the James Webb Space Telescope are looking at now. Right, okay, so that's all I wanted to say. I'm going to quickly run through my conclusions, which will just be a couple of key plots. So first of all, to remind you, we've got in our own solar system, we've got the asteroid belt in the inner regions, and we've got the Kuiper belt in the outer regions. And we can see things that look like the Kuiper belt in extrasolar systems as well. And these are some of these images here. And then if we want to picture what's happening in these belts, basically this is the single image to take away with you. Okay, so we've got our star, orbiting our star, we have this belt of planetesimals, so asteroids and comets. They're colliding together, and when they collide, they release dust, and the dust is what we see. And then finally, these belts can interact with planets that are nearby, and that can impart shapes and features on the belts, which can allow us to detect the planets, even if we can't see them directly. Okay, so that's my sort of whistle-stop tour of extrasolar Kuiper belts. I hope it's been understandable and interesting. I'm happy now to take any other questions. Thank you.
Well, thank you, Tim. I find that fascinating. And I've been saying in our kind of introductions to our earlier meetings for several months now, how interesting dust and debris must be. And you've absolutely proved it. So perhaps I can jump the question queue and ask, do we ever build physical models of these, or would they not add anything to our data simulations or software simulations?
We do. So, but we're limited in what we can build. So, in one of the sort of cooler sounding experiments, what happens is we want to know a little bit about how these objects fragment. So I mentioned that we've got these sort of various theoretical models, which I talked about earlier, which is like the material strength. So small things are strong and big things are strong, and things in the middle are about 100 meters in size, they're weaker. We want to know when you have these objects colliding with each other, how exactly do they break apart? Because it turns out that's really important. So do they, for example, completely shatter into just loads of dust? Or do they break roughly in half and you produce a little bit of dust or something like that? And that's really important because it means that from our images of the dust, we can infer how much material there is in the larger bodies. Because because we can't see the larger bodies directly, we need to somehow relate the dust to it. Okay, so we really need to know what fraction of this material is released as dust in these collisions. So physically, what people do, and they particularly do this in Germany, there's one in Freiburg, where basically they have these essentially guns which are pointed at each other, and you put rocks in the guns and you launch the rocks at each other. And then you have in the center, in a sort of collision chamber, you have a very high speed camera, and you also have a series of very fine nets of different grades. And what this allows you to do is it allows you to literally observe one of these collisions at the speeds that they would actually happen. Because these are, say minimum of 100 meters a second, but could be faster. So these are almost like bullets hitting each other. And they allow you to see exactly how these objects fragment. And more importantly, they allow you to show you what material comes off them. So like how many big grains, how many small grains, that sort of thing. So that's the closest I think we have to physical models, if that makes sense. That's the most real world thing that we have. But obviously you're quite limited because you can't launch sort of 2 kilometer sized objects at each other. So that's where you have to sort of calibrate the models with theory. But you can calibrate them at sort of, yes, centimeter sized objects and that sort of thing.
Cool, thank you. We'll hand back to you to run the rest of the questions.
Excellent. That was fantastic, Tim. Brilliant stuff. Mark, if you'd like to unmute and ask your question, which you gave at near the start of the talk, please.
Thank you. An excellent talk. Lots of new ideas I hadn't thought about. It's really an amateur question, I suppose, is that we do a lot of comet observations in our society, as do a lot of amateurs. And there must be quite a body of data out there from amateurs. Is that used to inform your observations or your understanding of external Kuiper belts, or is our Kuiper belt too different, as you've already hinted at, or you're looking at much larger scale objects as well? So is this of any use?
It's definitely of use, yes. So what we've kind of done here is we've almost got 2 sets of data at opposite ends of the scale, and we're trying to meet in the middle. So we've got the solar system data, as you've mentioned, where we can see individual comets and things like that, but it's harder to zoom out in the solar system to see what the solar system would look like from an external star. And then similarly, for these Kuiper belts, these extrasolar Kuiper belts, we can see the Kuiper belt, but we can't really see the objects individually inside them. Okay, so what we try to do repeatedly is take the data from our solar system, so for example, things like what comet tails look like, or like what the composition of comets are, or what the size distribution of the grains coming off the comets are. They all come from these sort of observations that you're talking about. And then we've sort of basically had to take those models, and then assuming that these extrasolar Kuiper belts aren't completely different fundamentally to ours, attempted to build a picture of what's happening in those belts as well. Okay, so that's what we started doing a long time ago. So this field was basically born in the 80s with the first observations of extrasolar Kuiper belts. Now things have got a little bit more advanced. So what I've not mentioned at all in this talk is I've talked about the dust, but we can actually also see gas in these systems as well. So we think what's happening is that there's things like ice that are locked up inside the comet. When they collide with each other, that ice is suddenly exposed to the heat and the light, and so that basically boils away into space. We can now see that, we can detect it. And what that allows us to do is it allows us to test, for example, whether these extrasolar comets have the same composition as the comets that you're talking about in the solar system. And the answer so far, we don't have a huge amount of data, but it looks pretty consistent so far. So it looks like these comets are made of roughly the same fractions of like rock and ice and things like that we get in our own solar system. But it's quite early days here. It's only been over the past sort of 5 years or so that people have been able to do this properly. 5-10 years. So yeah, so basically we are using both, and there's a gap in between that we have to just extrapolate a little bit, but we're slowly eating into that gap a little bit.
Thank you. So we'll keep on observing them then, yes.
Definitely keep on observing. They're super useful. Yeah.
Okay, Mike, if you could unmute and ask your couple of questions, please.
Yeah, thanks. Tim, that was great. You can tell I enjoyed it because I've got 2 questions.
Okay.
The first was just a simple one. I'm not sure of the exact numbers, but I recall about 6,000 directly detected exoplanets. Just curious as to how many we've added with this inference technique.
Yes. Okay. So to give you a little bit of context, in terms of how many of these belts we've directly imaged, so ones like the pictures I've shown you where you can actually see them, that's probably of order 100, I'll say.
Okay.
So, and for all of them, they've got completely different, in fact, I've got it on here, they've got different sort of resolutions and things like that. So some of them look really refined, some of them look like blobs. You can try and use this inference technique for all of them. Just like the simplest thing to do is basically to say something like, okay, well, let's just say at the inner edge of each of these belts is going to have a planet, like Neptune is set in the inner edge of the Kuiper belt. So if you do that, then you're going to add on of order like 100 or a few hundred or something like that to this. But in terms of the ones that have got the really detailed data, like these ones, where you can actually produce a really good dynamical model, you're probably just in the tens there. So you're not going to be taking your 6,000 exoplanets and then suddenly adding another 6,000 from your Kuiper belts. It's going to be of order like 100 that you can do roughly, and then it's going to be tens that you can do well. But the important thing, though, is that that's still really the only way to do it in the outer regions of the systems, except for except for really big objects.
Okay.
So it's still a probe, even though it's not applicable to every star.
Cool. And the second question, which sort of occurred to me just during the talk, is if you look at the timescale for sweeping out the dust, what can you infer about the collision processes for generating new dust to make the Kuiper belts last for, tens of millions of years?
Yeah, exactly. Yeah. So it really is billions of years. So for example, let's see. I think this system here, I can't remember its exact age, but that's something like 1 billion years, I think, or something like that. So yeah. So to answer the question, first of all, the rough lifetime of a dust grain in one of these belts is about 1 million years. Okay. And we need it to last like 1 billion years to explain some of these observations. So we know straight away this can't just be dust that's left over from planet formation, because it would have just gone by now. It has to be continually produced.
So it almost has to balance the sweep out rate, basically.
Well, yeah. Well, it doesn't quite have to balance it, because it actually fails to balance it. Because what happens is, do you remember the plot I showed earlier where it had the systems getting fainter over time? So at first there's loads of dust, and then that dust starts to get blown away. And then there's slightly less dust. There's still collisions going on, but they're not able to keep up with the rate at which the dust is being blown out. So it means that you get fainter over time. But what you can do, though, as you've sort of suggested, is you can take your knowledge of how long the dust should last, and that basically gives you the dust release rate. Okay, it tells you how much dust is being released at that particular moment in time. And that tells you how much dust is released in bodies, like from collisions with bodies that are slightly larger than the dust, right? Because you need bodies that are bigger than the dust to be colliding, even though you can't see them, to release the dust itself. And it actually turns out it's slightly better than that, because we actually have very good models which are calibrated with these gun tests and things like that. We have very good models now for how these objects collide and what dust is released. And what that actually means is that we have quite a good knowledge that let's say we can see this much mass, like a certain amount of mass in like millimeter-sized dust grains. We can actually say with reasonable certainty, okay, well, this means that we've got to have this much mass in kilometer-sized objects or 10-kilometer-sized objects and stuff like that. And that comes from, as you say, that comes from basically the dust replenishment rate that we're observing.
So you can infer the particle size distribution in the Kuiper belt.
Exactly. The difficulty, though, is we don't know where to stop, because we basically get a line that says, okay, for every size that we increase, we go down in the number of bodies by like a factor of 100 or something like that. But we don't know if we can take this dust and extrapolate it all the way up to like Pluto-sized objects. Actually, it turns out we think we've got evidence that the biggest bodies in some of these disks are much smaller than Pluto. So actually, Pluto might be unusually big, and most of these disks might have kilometer-sized objects. We don't know where to stop the extrapolation, but the size distribution itself seems pretty solid.
Cool. Really interesting. Thanks.
Anyways.
Jim, if you'd like to ask your second question, unmute, please, that'd be great.
Yeah, thanks. Like Mike said, it's a great talk, and questions similar, well, adjacent to Mike's one. So given that our Kuiper belt would be too faint to observe if it's extrasolar, does that imply these radio ones that we see on the slide are of a fairly young system, or does the type of star in the system, in terms of how much solar wind it generates, imply, does that correlate with what you can observe?
It's an excellent question. And the answer is a bit of everything that you said, plus some more things. So one thing that we have to caveat straight away is that our observations are incredibly biased because of what we can detect. So we're basically sensitive to detecting the biggest, brightest disks. And many of the ones I showed you are in this part of the plot because they're brightest, so they're easiest to observe. So what that means is that I'm mainly showing you pictures of young systems because they've got the brightest disks. Okay. So that's one point. Another point that you mentioned is to do with the type of star. Again, the bigger the star, the brighter the star, and the brighter the disk. So we're also biased to be looking at disks around the brightest stars, around like A-type stars that have got masses of twice the mass of the sun, for example. We can see them around solar type stars as well, around sun-like stars, but they're fainter. So usually the most spectacular images you'll see will be young, bright stars. But even factoring all that in, you can see that our asteroid belt and our Kuiper belt is still way lower than even the faintest one that we can see in an extrasolar system. So we really are truly much fainter than these ones. I mentioned before that it could be we've got a broad distribution of these and we can only see the very brightest objects, and our asteroid belt and our Kuiper belt are quite typical. That's a possibility. To put some context in that, so we detect these belts around 25% of stars. So we're seeing the brightest, like if they're uniformly distributed, we're basically seeing the brightest 25% of them. So that's one possibility, that 75% of them are down here, like the Kuiper belt. The other possibility, though, is that the Kuiper belt's weird, and we have evidence for this. So the evidence is we know that Neptune, early on in the lifetime of the solar system, crashed into the Kuiper belt. And when it crashed into the Kuiper belt, it ejected a lot of material, and the Kuiper belt will have decreased in mass quite dramatically. So to give you some context there, the models that we have suggest that the early Kuiper belt had a mass of maybe 30 times the mass of the Earth. Okay, and that puts it in line with these bright ones that we see. But then Neptune crashed into the Kuiper belt, it ejected loads of the mass, and now the Kuiper belt's got a mass that's only 1% that of the Earth. So it's lost a huge, huge fraction of its initial mass. We have direct evidence for this in the orbits of Kuiper Belt bodies. I haven't got time to talk about it today, but basically you can look at the Kuiper Belt orbit so you can see that Neptune's migrated in the past and has crashed into it in the past. So that's potentially a reason why the Kuiper Belt might not be typical. It might be that it should be a lot brighter, but a lot of it was ejected by Neptune early on. And it might be that these bright belts just haven't had a planet fly into them, whereas ours has. So there's evidence in both directions, basically.
Yeah, thank you.
Were there the other questions? Sorry, Will.
Oh, apologies there. I think you've just answered up one of our questions from Fornalas4385 on YouTube there, who was asking why you see our Kuiper belt as being weird. So it's great you've answered that with the with Neptune effect of crashing in it. We got a final question from Norman. If you could unmute and please ask.
Yeah. So the question I've written out is the apparent sort of well-defined ring an optical illusion just because you're looking at the edge of a sort of a roughly spherical or elliptical shell, ellipsoidal shell, or is it that they are well-defined rings and that's part of the process of them being produced, and are they being shepherded like Saturn's rings with lots and lots of presumably quite significant sized bodies?
Yes, so that's a great question. So and the answer is a slight cop-out answer, but it's basically a bit of both. So what I haven't got any plots of it here. But what we can do now is we've got images that are high enough resolution that we can measure what we'd call the sharpness of the edge. So if you imagine like a brick wall, there's basically like nothing, 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 and then suddenly there's brick. That would be a very sharp edge. Whereas if you imagine like a shallow hill or something like that, that's a much shallower edge. we've got some disks that have very sharp inner edges, and that kind of looks like, for example, a little bit like what the Kuiper Belt looks like. And so that is evidence that you might have a planet which is located at the inner edge of this disk. And it's basically, as you say, shepherding it, or it's sort of carving out its inner edge and setting its location. You have other disks, though, that have much smoother edges and don't really look like they're sculpted by planets at all. So what that tells you is that either planets aren't there, or that, for example, the planets were there in the past and have moved away, because that's also possible as well. We talked about Neptune moving around outwards. Other planets could have moved inwards, for example. So it might be that you originally had a planet there and it's now gone. But yeah, so for example, this object here, I believe, has a relatively sharp edge. So this one probably is as it looks, that there probably is sort of planet there. But some of them, I don't know if there's a good, I think this one's a good example, though you can't really see it here. This one has quite a sharp inner edge, but then a much smoother, more gradual outer edge. So what that probably tells you is there may be a planet at the inner edge, but not at the outer edge of the system. We could potentially have shepherding objects, as you mentioned, like Saturn's rings. Generally, for this to work, you need those planets to be at these distances. You need them to be Neptunes or larger. So to give you some context, we can't directly see Neptunes with James Webb. They're too small. But what we can see are Jupiters. Okay. So we can, in some of these cases, say there's not one big Jupiter that's at the inner edge of these disks, but we would predict that it wouldn't be Jupiters, but it'd be Neptunes that are located there. And we can't rule them out yet observationally. So yeah, so it's a little bit of both. In some cases, we think the planets are there because we see these very sharp edges. Generally, though, we don't think we've got planets either side of the disk. Generally, we're more thinking of planets at the inner edge of the disk, like Neptune is, and then the outer edge, that's a little bit more free, basically because it gets harder and harder to form planets the further away from the star you are. That was quite a long answer. Did that answer your question, Norman?
Yeah, no, that's great. Thanks. Yeah, I was sort of thinking, gosh, some of those look like very, very tight rings, almost like a planet that's broken up and then sort of managed to sort of get itself smeared out along its own orbit or something.
Yes. So people have tried that model actually before for these rings when they first detected them, but the problem is we just detect too many of them. We see them around like 25% of stars, so it's hard to imagine that each one's a broken up planet because you need that planet to have broken up really recently for that dust to still be there. So it'd be too big a coincidence if like every system basically has one of them. But yeah, some of them are very thin rings, but some of them are much more sort of extended as well.
Thank you.
No worries.
Excellent. We'll just move over to a question from one of our YouTube followers, Martin Pride 609, who asks, could be a tough one, this actually, is there any indication that Neptune crashing into the belt was before, after, or the cause of the late heavy bombardment?
Okay, so in the original models, this was actually part of the justification for the late heavy bombardment. So the original motivation for what we refer to as the Nice model, because it was originally concocted in Nice in France. In that model, you had these various lines of evidence in the solar system. One of them was the late heavy bombardment, which is basically where we have evidence that at a certain point early on in the solar system's life, suddenly loads of stuff hit the Earth. Okay, it went from a period of not much stuff hitting it to loads of stuff hitting it. That was one of the pieces of evidence that we had to try and concoct what had happened in the early solar system. And so you're exactly right. In the early model, in the Nice model, what basically happens is, so you've got the four giant planets, Jupiter and Saturn basically get dynamically unstable, and this instability, because they're so massive, is able to massively perturb Uranus and Neptune ends up flying into the belt. It scatters and ejects a lot of material from the belt, but it also throws stuff inwards as well. It throws stuff both outwards and inwards. And the idea was that this was the material that came inwards and formed the late heavy bombardment. Basically, the disruption of the Kuiper Belt was the late heavy bombardment. So that was the idea. That model is not, I don't want to say it's gone out of favor because it's still a very good model, but there's been other sort of refinements and things like that to it. And actually now there's questions about quite how big the late heavy bombardment was. In fact, I've heard a quote that said that the late heavy bombardment was neither late nor heavy. So I think the jury's actually a little bit out on that one about what's actually happened. But yeah, certainly in terms of the conventional late heavy bombardment that we often picture, that was the direct cause of Neptune flying into the Kuiper Belt and then throwing lots of material inwards.
Excellent. That's very interesting. Fabulous talk there. I think that's all the questions, Neil, from both Zoom and YouTube. So over to yourself.
Well, thank you, Will. I think that's a great segue into my kind of closing statement. We talked before the start of the evening, and I decided not to promise that, Tim, you would get a load of questions, but obviously I needn't have worried. I could have quite happily jinxed the evening. So please can we all come off mute and thank Tim for his amazing talk and for answering all of our questions.
Thank you, everyone.
Thank you.
Tim, you're welcome to stick around and hear about what we've got coming up next. I will just share my screen and take us through to the end of the evening.
Yep, I'll stick around.
Cool. Okay, so to close out the evening, let's take a look at what we have coming up in the next few months. So this was our final event in 2025, and as I've said, what an excellent way to finish the year. So thanks again, Tim, for joining this evening and for such an interesting talk. We now have a couple of weeks off over the festive season. There may still be some newsletters, so keep a lookout for those, especially if you're intending to enter the Image of the Year competition. Normal service is resumed in January 26. And yet again, note that our first meeting in the month is not on the first Friday in the month. Our main hybrid meeting is on Friday the 9th of January. And in a talk entitled Growing Up in a Rowdy Household, Moira Jardine, Professor of Astronomy at the University of St Andrews, will look at the impact of stars on their planets, especially early in their lives when the star is most active. So that promises to be a fascinating talk as well. And then on Friday the 23rd of January, our mid-month meeting is the one that's been rescheduled from September. So Professor Claudia Durham's talk from Claudia from Imperial College London will share the secrets of gravity, the overarching miracle connecting everything we know and the reason that the universe itself can exist and evolve. So again, another fascinating talk. In other events, we have our members only online imaging and observing group meeting on Wednesday the 14th. And as usual, that will be hosted by David Brett. And looking ahead into February, our guest speaker on Friday the 6th at the AUC will be Ruth Borum, who is an Edinburgh tour guide and historian, and her talk has a working title of Moon Women. We'll get more details on that a little bit closer to the time. And the same applies to our mid-month meeting on Friday the 20th. The speaker is yet to be confirmed, so I'll share more information about these presenters and their talks next month. Our Imaging and Observing group meeting is on Wednesday the 11th. And just a reminder that all of the information about these events is available on the events calendar page of our website. So that brings us to the end of this evening's agenda, but we do have another event of note on Sunday, the winter solstice, or the shortest day. We'll have approximately 7 hours and 50 minutes of daylight on Sunday. So it's important to keep looking up while we can to observe and image the night sky as the nights begin to shorten. And finally, all that remains is for me to wish you a good night, clear skies, and a very Merry Christmas from the Society. Thank you very much.